Okay, let's unpack this. When you look around you, I mean, really look, the phone in your hand, the clean water from your tap, even the building you're in, you are looking at the practical, very real result of professional engineering and geoscience.
It's everywhere. The entire infrastructure of modern life, really.
Exactly. And today we're doing a deep dive into the absolute backbone of that infrastructure, the manufacturing and processing sectors. These industries, they're not just about making things, they're about this fundamental transformation of raw materials, from minerals in the earth to the products that drive our world.
It's a massive, complex system.
It is, and our goal today is to really get into the specifics. We want to synthesize the critical roles of engineers and geoscientists, look at the full product life cycle, and then really dissect the ethical demands that define professional practice today.
Which are becoming more and more important.
They really are. And on that note, if you are working to master this professional landscape and want to be prepared for these rigorous standards of practice, we invite you to subscribe right now. We cover essential content and professional standards to help you stay ahead of the curve and be successful on the NPPE exam. That's the standard for demonstrating professional knowledge across North America. So before we get into the different roles, we have to clarify the terminology. We often say manufacturing and processing like they're the same thing, but professionally, they're quite different, aren't they?
They are, and that distinction is, it's crucial. It really boils down to the form of the output. Manufacturing is all about the systematic production of finished goods.
Finished goods, so the end product.
Exactly. It involves taking materials that have already been refined and then using machinery, labor, design, fabrication, assembly, and of course rigorous testing to create a final product.
Okay, so we're talking about things like components for a car or medical devices, maybe circuit boards, the actual items.
Precisely. Manufacturing deals in these complex multi-component products. Now, processing, that's different. Processing focuses on transforming the raw materials into usable or refined forms.
Ah, so it's the step before manufacturing.
It's often much earlier in the value chain, yes. It's about taking something raw and changing it physically or chemically or even biologically into the inputs that manufacturing needs.
Can you give us an example of that, the scale of that change?
Sure. Think about copper ore. It comes out of a mine, as rock. Processing is the step where you smelt that ore using very complex chemical engineering to produce pure copper sheets or wires.
I see. So the ore is the raw material, the copper sheet is the processed material.
Exactly. Or think about crude oil. Processing is that huge industrial effort of refining it into gasoline or jet fuel or the feedstocks for plastics.
And what's so interesting there is that processing is really the point where geoscience, understanding where that ore or oil came from, has to perfectly mesh with engineering, designing the tech to transform it.
That's the perfect way to put it, like a critical intersection.
Which brings us to the specific roles. These two professions have to collaborate, but their jobs are very distinct. Where do engineers really focus their attention in these environments?
An engineer's focus is almost always on the system itself. In a manufacturing plant, they're designing the efficient workflows, they're optimizing the layout of the factory, and they're ensuring the whole plant operates safely and consistently.
And we're talking about some incredibly sophisticated systems, right?
Oh, absolutely. Their core functions include advanced process design creating systems that move materials with minimal waste. And a huge part of that now is automation.
Robotics, AI, that sort of thing.
Yes, integrating control systems, robotics, AI, to handle tasks that are either repetitive or just too dangerous for a person. And of course, they are the final authority on quality assurance, making sure every product meets every single safety and performance spec.
And it's so multidisciplinary. It's not just mechanical engineers building the machines.
Not at all. You have chemical engineers designing the reactions, electrical engineers managing the power systems, industrial engineers optimizing the flow. It's a complete convergence.
Okay, so if the engineer's focused on the system, what about the geoscientist?
The geoscientist's focus is on the material and its source, the Earth. You could say they're the gatekeepers of responsible sourcing and material quality.
So it's more than just finding the deposit. They're actually predicting how that resource will behave once it's in the plant.
That's exactly it. The first function is exploration. Yes, identifying viable deposits. But then, crucially, they determine the material's composition and predict its behavior. That knowledge is vital because it dictates the entire engineering design of the processing plant downstream.
If you don't know the chemistry of your feedstock, you can't build the right refinery.
You can't. And they're also essential for long-term planning. Like, where do you even build one of these massive facilities? They assess geological stability, the environmental baseline to minimize risk, and they manage the impact of the extraction and waste disposal right from the start.
Let's connect this to the bigger picture then, the entire life cycle. This really defines the professional's sphere of responsibility from cradle to grave. Can you walk us through that lifespan?
Of course, it always starts with stage one, raw material acquisition. This is pure geoscientific work mining, drilling, finding the resource. That material then moves into stage two, material processing. That's the first major engineering touch point.
Where the raw inputs are refined into something usable.
Correct. Steel, polymers, whatever it may be. Then we hit stage three, product design and manufacturing. This is where engineers use powerful tools, CAD, CAM, CNC machinery, robotics, to actually fabricate the item.
Which is then followed by what I assume is a critical step, stage 4, quality control.
Non-negotiable and incredibly rigorous, given the safety implications. Products have to meet performance, durability, safety metrics, often against global benchmarks like ISO 9001. Adhering to standards like ISO ASTM or CSA isn't just about making a good product, it's about public safety and global trust.
And that brings us to the modern imperative, doesn't it? Stage 5, distribution, use, and end-of-life management. We can't just throw things away anymore.
Absolutely not. And this is where professionals have to integrate circular economy principles. That means the product design back in stage 3 must now be designed for longevity, for easy repair, for disassembly, for high-value recovery. The whole take, make, dispose model is obsolete.
So professional success today isn't just about efficiency anymore, it's about impact. Sustainability and ethics are now really their key performance metrics. What are some of the key systems that professionals have to implement to meet this higher standard?
The shift has been profound. It's moving beyond just minimum compliance and towards active environmental stewardship. For example, implementing energy-efficient operations using cogeneration, where you capture waste heat from one process to power another, or developing closed-loop water recycling systems.
And I've heard about green chemistry as well.
Yes, that's a big one. Designing chemical processes that use less hazardous substances from the outset. But a key professional tool here is what we call life cycle thinking, or LCA.
Right. How does that actually work in practice? How does it guide decisions?
LCA is essential for ethical practice. It forces the professional to evaluate the environmental burden of a product across its entire existence. So you're not just counting the energy used in the factory, you're factoring in the impact of the raw material extraction, the transportation, the energy the product uses during its life, and what happens at the end. It helps you answer tough questions like, is it better to use a material that's more energy intensive to create but lasts twice as long?
And that leads directly into the circular economy. Your LCA should point you toward closed-loop systems.
It should. The goal is to design systems where the waste from one process becomes a valuable input for another. And beyond the environment, there's the huge aspect of social responsibility. Worker safety, fair labor conditions, ethical sourcing like avoiding conflict minerals, and proper, respectful engagement with local and indigenous communities.
The pace of change here is it's breathtaking. The whole concept of Industry 4.0. What are the emerging technologies that are completely reshaping how engineers and geoscientists work right now?
Industry 4.0 is really the merger of the physical and digital worlds. At its base, you have sophisticated automation and robotics. This enhances precision, sure, but it also takes workers out of high-risk environments, which is a massive boost for workplace safety.
And the materials themselves are changing too.
Dramatically. Huge developments in advanced materials, stronger, lighter substances like carbon fiber composites or nano-engineered alloys. These change the fundamental rules of design. But the real game changer is artificial intelligence and smart manufacturing.
How does that actually change what happens on the factory floor?
Well, AI analytics, combined with IoT sensors, the Internet of Things, allow machines to talk to each other in real time. This means the system can self-optimize, it can predict when a machine needs maintenance before it breaks, and it can self-correct for quality issues on the fly. It drastically cuts downtime and waste.
And that level of optimization must be critical for the climate goals the processing sector is facing. I mean, how does this help with decarbonization?
The pressure for decarbonization and clean processing is immense. We're seeing huge investment in carbon capture technologies, a major push toward electrified heat systems to replace fossil fuels in processes like smelting, and even research into using hydrogen as a clean fuel. These are the engineering solutions to global climate targets.
So given all this complexity, the speed of change, the huge ethical stakes, What does this all mean for someone practicing in these fields? For the professional on the ground?
It means that rigorous adherence to professional standards is not optional. It is absolutely paramount. These standards aren't just suggestions, they are the contract that professionals hold with the public. They represent accountability and a commitment to protecting people.
What does that rigor look like in practical terms?
It means deep compliance across many areas, mandatory adherence to engineering codes of practice, comprehensive environmental regulations on emissions and waste, occupational health and safety laws, and of course the international technical standards we talked about, ISO, ASTM, CSA, which ensure products are safe and reliable worldwide.
That is a huge burden of knowledge to maintain.
It is, and that's why the core ethical responsibilities have to underpin everything. The number one duty is always the protection of the public. Always. That requires unwavering honesty and integrity, proactive environmental responsibility, and critically, continuous learning. With the pace of Industry 4.0, lifelong professional development isn't just a good idea, it's an ethical necessity to remain competent.
So we've really seen that manufacturing and processing are so much more than just economic engines. They are this frontline intersection of technology, rigorous standards, and deep ethical commitments. They fund R&D, they create jobs, and they provide the very foundation for every other sector of our society.
That's right. Professionals in these fields are tasked with ensuring industrial growth benefits all of society, both sustainably and equitably. So as technology speeds up, and you see the power of tools like smart manufacturing and life cycle assessment, consider this. How will you, in your role, actively push your organization closer to a truly self-sustaining circular economy model?
And if you are seeking to deepen your understanding of these professional, ethical, and regulatory responsibilities, which is essential knowledge for success, make sure you subscribe now to hear more about how to be successful on the NPPE exam.